It's a great pleasure to have you again with us at the next installment of Faraway Fourier Talks. Today's speaker, Professor Carlos Cabrelli, and he will talk about frame constructions. Carlos, if you'd like to share your screen, and in the meantime, I would like to ask everyone to, while Carlos is speaking. And if you have any questions, you can unmute yourself to ask those questions. Carlos, the audience is yours.
Okay. Thank you very much for the introduction, and thank you for inviting me to this conference. Before I start, I wanted to thank Jean and all his team for keeping alive this seminar that is really my FFT workshop that now it transformed in this seminar. I think it's very good and very, very important. So today I'm going to talk about some work that we started several years ago. We did it in several stages with different people. So let me first show the people that collaborate with me in this work. Okay, Akran Al-Drubi from Vanderbilt, Ursula Molter from Buenos Aires, my former student Victoria Paternostro. Now it's a professor at the University of Buenos Aires. Armenak Petrosian from Georgia Tech. And Friedrich Philipp, that was a postdoc in Buenos Aires, and now he has a position in Ilmenau University. Before he has visiting with a postdoc with GetFinder. And Daniel Suarez, that is a colleague of us in Buenos Aires. And Sui Tang, that now he was a student of Akran and now is in UC Santa Barbara. Okay. This talk is going to be about a very simple mathematical question. Okay, let H be a complex separable Hilbert space, T a bounded operator on H to H, and you take a vector in H. And so the question is, if you take the iteration of F through some index set that could be infinite or finite, we ask whether this is a frame of H. So condition on operator T and the function F such that this is a frame. So that's a question that we are going to talk today about. So the motivation for this question came from a problem that is most of you probably know, that is called the dynamical sampling problem. Since there are probably some people that didn't hear about that, so I will give some insight in what is this problem. So assume that you have a signal, but you don't know that signal, and you have some information in terms of samples or some average samples, and this information is not enough to reconstruct the function. So you cannot get the function back. So we had the extra hypothesis that the signal F evolves in time, like in dynamical system. And evolves in time through an evolution operator we are calling T, that goes from the space where the signal lives. And so you have the different, in discrete time, no? We have the different signals that are evolving from the original one. So the question that we ask is if we sample the evolved signal in the same locations, if with this extra information we now can reconstruct our original function F. So assume that we have F is an initial state of a dynamical system, and so you have some sensors, and you activate this sensor at times 0, and then time 1, and time 2, and so on. So you have not enough sensors, then probably using information from the future, you can get the function f. That's what essentially is the dynamical sampling problem. So this idea appeared firstly in a couple of papers of Betterly and some co-authors and Lu, and they used the dynamical system was controlled by the heat equation. And then Adrubi, his student Jackie Davis and Ilya Crystal wrote a couple of papers for the special case that the evolution operator was a semi-discrete convolution. Okay, so here I make a little picture that you have the original function f, you know this function in these points, or you have this function g that's some kind of bump function located in these positions, and then you sample f here, then you sample t of f, and then you sample t square of f, and so on. So we were I was in the jury of Jackie Davis' presentation, so I was start to get a little bit knowledge of this problem. We were in Ursula in Nashville visiting Akron at that time, and so we start to think in this problem. So if you look, if you look at the conditions in order that we can recover the function, you see that we need we have this measurement that are controlled by these GK, the bump functions, with against iteration of Tj of f. But if we put the iteration in the other side, in the right, data joint, so you see that the condition to get f is exactly that this iteration of GK is a frame of the space. So that the usual requirement to get a stable reconstruction of f. So we need to that the iteration of the joint of T, that could be also we can call it T if we start with a joint, is a frame. So the dynamical sampling problem becomes a problem of trying to find frames of iterations of some operator in the Hilbert space. So that's a problem that I mentioned when we started this talk. So we decided, I read the other day biography of Helmont, and they say that Helmont used to say that when you have a problem in operator theory, the first thing you have to do is think in the dimensional, the finite dimensional case. We didn't read the Helmont advice at this moment, but we start with the final dimensional case. So just to get some insight of the problem, let's get even the simplest case that we have a matrix, linear transformation in a finite dimensional vector space, and assume that it's diagonal. For example, assume that the eigenvalues are lambda, lambda, and mu in 3 by 3. And two of the eigenvalues are the same, so have multiplicity 2. So you take a vector x, and you never get a frame iterating A. For any x, okay? So one thing that I want to observe here that we use in the rest of the talk is that it's not necessary to iterate A more than the dimension -1, because A to the cube is a combination of the identity A and A squared, okay? So we iterate until 2. For any x, this doesn't work. Why this happen? Because when you multiply by a diagonal matrix, what you get is a vector x multiplied by lambda, lambda, mu. So the vector that you get is lambda, lambda, mu lambda square, mu. So the first two components of x get multiplied by lambda. So you get linear dependent vectors in the two first components. So that's the reason why this never is complete. And for finite dimension, to be a frame means to be complete. So we need to iterate here at least two vectors. This is some idea that is going to be used later. But for example, if the eigenvalues are all different, we can use this vector 1, 1, 1. And this is going to be when you get the columns vectors in a matrix. This is a van der Monde matrix with all the powers of the eigenvalue. Since eigenvalues are different, this is invertible, and you can get x. But if in place of 1, 1, 1, you take 1, 0, 1, this is not y, a y, and a square y is not complete. So it's not that for any x you will get that. So this is just to give some insight in what kind of problem we can encounter when we try to do this problem. So after work a little bit, we proved that if linear transformation have a vector so that iteration is complete, then any similar matrix have the same property. So it's enough, we can reduce the problem to study canonical form of the matrix, to study the problem in a canonical form, for example, the Jordan form. That's what we did with Akran, Ursula, and the student. And so we got this here, that essentially what it says is that in order that this is a frame, if you project the vector that you iterate, okay, over the, in place here, since the matrix is not diagonal, if the matrix were diagonal, we need to have the eigenspaces, but since it's not diagonal, we take for each eigenvalue, and for each block, you have a cyclic vector. So we take the span of the cyclic vector. This is going to be this space Vj, and so the projection. In this case, is the oblique projection of the span of Z that are the functions that we iterate have to be on the space. So that's conditions are necessary and sufficient. Later on, with Fritz Phillips, he found that we can replace the oblique projection with orthogonal projection if we, in place to use T, we took T star. So this for application could be a little bit more easier to use. So other than trying to get an algorithm for applications, we finished with this finite dimensional case. So we move to the infinite dimensional case. So again, we start with the simplest case. We assume that T is a self-adjoint bounded operator that have an orthogonal basis of eigenvector. It's a diagonalizer. We want to translate the results in finite dimension to infinite dimension. So we assume that T is have eigenvalues lambda k, and that's an orthogonal projection pk over the eigenspaces. And to make things even simpler, we assume that the Hilbert space is L2 of n, or sequences. Okay. So we take G to be a set of vectors in H. So for completeness, it's the same condition as in finite dimensional case. You need that the projections over the eigenspaces of the vectors that you iterate is a frame. This has to happen for each of the eigenvalues. However, we realize that okay, it's very easy to get complete systems, but it's never going to be minimal. I mean, the iterations in n star. When we start in 0 and go forward, sorry, you will never get a minimal system. The reason why this, well, the proof that we found for that is that when you take t to the j, you can think that this is a monomial x to the j and replace x by t, okay? So for the monomials x to the j, we have this theorem of Munsak that sets us as you take all the powers. You need to have all the natural numbers here in the powers. You can have a subsequence, and if this subsequence, the inverse, diverse when you sum it, then you still get a complete system in the space of the continuous functions in the 0, 1 with a uniform matrix. So you can translate this result to the iteration of t, and you get this property that is never meaning. So this in particular means that you can never get a basis using orbit of operators. Here we had, sorry. I think we have, okay. We never have basis of 8, sorry. Okay, so when we realize that this happened, we say, well, what about if we try with frames? So we, in this setting of self-adjoint bounded operator with an orthogonal basis of eigenvector, we start to get necessary conditions. Okay, so we assume that this orbit is just, and we start with just one function. We iterate just one function first to make it even simpler. So we assume that there is a function that the orbit is a frame of H. So the first thing we got is that the eigenvalues of T, remember that T was a diagonalizable operator, so the eigenvalues have to have modulus less than 1. In this case, the eigenvalues are reals because the operator is self-adjoint, but anyway, they have to have modulus less than 1. The multiplicity of the eigenvalue has to be 1. It cannot be bigger, cannot be 0, okay? So these are so far necessary conditions. So the other necessary condition we got is that the eigenvalues have to have, the absolute values have to be convergent and have to be convergent to 1. And finally, the vector that we iterate have to have this property. I mean, the gk here is a k component. Remember that these are sequences, okay? In the indexes by the natural number. So the k component, the absolute value, divided by the associated eigenvalue, square, modulo square root, has to be between two constants. So if you move the square root and multiply C2 and C1 by this square root, then you get that gk is between the sum of these eigenvalues. And since gk is in L2, then you get that the sum that I wrote here is finite. This sum is finite. And this says that we will use it later, that the lambda k is a Blaschke sequence, okay? That the product of C minus lambda k is going to converge. So these conditions, 1, 2, 3, and 4, are only necessary conditions, and we realized that was not sufficient. So at that point, we were thinking that there was not frames at all for this iteration. So we came back from Nashville, was the time that we can fly. And well, the problem was standing for some time. And I was working with some colleagues in another problem that involves quasi-crystals and so on. So one day I say, well, I asked some of them, what happened, you know, if we can invert this Gramian, because here you have to think that as in the finite dimensional case, we have a diagonal operator, and you can think this as an infinite matrix, and you multiply by a sequence, and then you multiply the square by a sequence, and so on. You put this as a columns of infinite matrix, you get kind of Vandermonde matrix infinite dimension. And we need that this matrix times that joint is bounded below. And this matrix is usually called the Gramian of the system. So surprisingly, my colleagues say, yes, I know how to bound this product. And it was late at night. He went home, I went home, and then he called me back by phone and sent me the suggestion. And the suggestion was that the missing condition to be a sufficient condition was that the sequence of eigenvalues were an interpolation sequence in the Hardy space of the disk. I mean, I mentioned a minute ago that when you iterate the multiplication of the diagonal matrix time a vector, you get these columns of all the eigenvalues at different powers. If you look at the rows of this infinite matrix, you get in each row you get one eigenvalue and all its powers. So this you can think as a coefficient of analytic function. And this is actually the kernel of the Hardy space, in the Hardy space, that is a reproductive kernel Hilbert space. And that gives you the function that is the evaluation in this eigenvalue. So the condition that these were interpolation sequence is that the these rows that we map in the Hardy space need to be resequenced. And then the good news is that the interpolation sequences in the Hardy space were completely characterized by Carlson in 1958. So this was a really, really good thing. This guy that made the connection was Jorge Antesana, some of you probably know. So let me say what Carlson theorem says is that if you have a sequence in the unit disk, open unit disk, so you have what is called the pseudo hyperbolic metric in D, and the distance between 2 points in the disk is defined. I think I have in the next slide here. That's the pseudometric pseudo hyperbolic matrix. So we say that a set of points in the open unit disk is separated if the distance between two of them different is bigger than c, some constant bigger than 0. Okay, and we say that it's uniformly separated if the distance between one fixed of the point to all of the other ones is bigger than a constant, and infimum, this constant is uniform, infimum is still bigger than 0. That condition was known to be, I think, necessary. Carlson proved that was sufficient to be an interpolation sequence. So the Carlson theorem says that a sequence is interpolating if and only if this property is satisfied. So what the conclusion of that is that you iterate in an infinite dimensional space in this case, L2 of n star or n, a diagonal operator or diagonalizable operator. So what you need is that the diagonal, the elements in the diagonal, the eigenvalues, have to satisfy this Carlson condition, and this is necessary and sufficient to get a frame in this setting. So the theorem is that you have an operator D that is a sum in J of lambda J Pj, where the Pj's have rank 1, and Bk, that is going to be the vector that we iterate, is a vector in L2, and then the iteration is framed if and only if the eigenvalues are smaller than 1 for all k, converts to 1 in absolute value, and satisfies the Carlson condition, and the vectors that we need to get a frame have to satisfy this property. Okay, so we finish with this. We were very happy that finally we got frame, but the setting was very restrictive because they were self-adjoint, and I have to have this basis of eigenvectors. So what happened with a little bit more general operators? So the next step was to look at normal operators in place of self-adjoint in any general separable Hilbert space. So now we look at the case where H is a general Hilbert space and T is a bounded normal operator and G is a vector in H. Always, again, one vector. We iterate one vector. I mean, we have one orbit on it. So at that moment, Akran has a very good student that is Armenak Petrosian, and we were working with Ursula, Akran, and him to try to see what happened with this case. And the good news was that if it was a necessary condition for a normal bounded operator that they have an orbit that is a frame, is that it has to be diagonal. So the only difference here that the lambda j could be complex. But this theorem, it was very good because we can use now the other theorem, and then we translate the result that we had for self-adjoint operator to this case. So the only normal bounded operator that give a frame with one orbit are the ones that are diagonalized. So we have a similar theorem. Now we start that the T is a bounded normal operator and they have an orbit that is a frame, if and only if, well, it's diagonal, or diagonalizable, and these are the conditions that we saw before in the other side. So then what's the next step here? So we only consider just one orbit. What happens if we have now a finite number of orbits? Can you get the frame? Can we characterize when? Because we can always, with several orbits, we know we can apply this theorem and get one frame, and then the other could be anything, unless you have to be Bessel. That's enough. So, but characterize when we have a finite number of vectors and the iteration of T on all these vectors generate a frame. We thought that was a simple generalization of this case, and actually it was harder than this case. So now we assume that T is a operator bounded normal from H to H, and we have now a finite number of vectors. So when is this a frame? Well, at this time, we were in Buenos Aires, and Fritz Phillips was doing a postdoc in Berlin with Gita Coutinho, and he came to Buenos Aires for another postdoc. So we decided to go with this project with him, Victoria Paternostro and Ursula Molt. So we're working hard in that, and we got a theorem with necessary and sufficient conditions, and it was very hard the part of eigenvalues because what we finally got is that the sequence of eigenvalues, sorry, have to be a union of interpolating sequences, not necessarily at most the number of vectors that we iterate. Could be less. But you have this problem that you have several sequence of vectors, and I mean, if a finite number, and if you take the union, it's always a frame. But what happens if none of them, for example, is a frame, but maybe the union, yes, is a frame. So that's the difficult part, and that's really was really pain to try to realize what happened here. So we got this theorem. The theorem says we have the index set, that the index of the vectors we iterate is finite. So the iteration of all these the functions with index in I, for starting with n bigger than 0, is a frame for H if and only if, well, this is the same than before. It has to be diagonal, but now the eigenspaces could be at most, the dimension could be at most of the size of the index set I. The set of eigenvalues, as I mentioned, has to be a union of at most cardinal of I interpolating sequences. And then the condition 3 here is the one that replaced, the condition 3 is for completeness. This what it says is that the projection of the vectors over piece of J is an orthogonal projection over the eigenspace. So when you project all these vectors and multiply by an H in the span, this is a frame actually, but the frame constant has to have certain uniformity. And finally, we get this 4 condition that was a little bit, it came up doing calculation, but we didn't really, we think that it's not very practical. See, in some sense, what it's saying here is the synthesis operator can cover the whole space. The rank is the whole space. What this is a condition to be a frame, but what we have here is that they have to exist in the Hardy space function phi that actually interpolate the sequence that we use for the synthesis operator. Again, the Hardy space was present here. So recently, we have this our colleague that I mentioned before, Daniel Suarez. He's a specialist in analytic function theory. He was not happy with this condition. He listened to talk about this. So we started to work with him to try to get a more geometrical condition. And we got another condition that replaced 3 and 4 using all the characterization of subspaces chief invariant in the Hardy space, but I don't want to talk too much about this because it's very technical and I don't have enough time. So what now that we have the condition for normal operators. What happened for operators, for general operators, that not necessarily normal. So for that case, I want to introduce some notation. Consider the triple TAG, where H is a Hilbert space. Always the spaces that we get are separables in order to get a frame. T is a bounded operator, and G is a vector in H, and assume that the iterations starting in 0 is a frame. So the idea here was to find a triple with some operator A, some subspace eta, and some function phi. But I mean, we wanted to get a kind of model triple that every other triple of an operator in Hilbert space and a function is somehow isomorphic to this triple. So we will ask that the subspace, this Hilbert space is going to be the subspace of some other Hilbert space. It has to belong to certain classes that I'm going to describe now. The operator A from eta to eta is going to be bounded operator, also with special characterization, and the function phi is a function in eta, and we want is that eta and H are isomorphic, not isometric, but isomorphic, and A and T, these operators, are similar in the sense that T is some invertible operator times A times the inverse, and phi and G are just the image of one to the other using the same isomorphism. So that's the idea for the general operator. So let me mention now that parallel to our work in this last work for the final number of generator, Ole Christensen, at that moment, his student, start to consider as a problem that was similar to the dynamical sampling problem, but not exactly the same. He was asking this following question: if you have a Hilbert space and you have a frame, not a frame of iteration, you have a frame, when an operator exists that you iterate the operator in some of in the first element of the frame, for example, the frame starts indexing in 1 or in 0, then you iterate that the frame is the iteration of some operator T. So he was looking at that kind of problem. I think he visited us in Buenos Aires. He was given some course in some province about these kind of things. But I am not going to talk too much about his work because it's several papers on that. But I just want to get some thing that he realized. And what he observed was that if you have that the iterations of the operator T is now a general operator, no condition on T. And so you take the iteration of T, and this is a frame and some vector G. So if you take the synthesis operator, that is the one that is described here, this is the sum, you take a sequence on L2 and you take the sum of Aj, Tj of G, the kernel of the synthesis operator lives in L2 of n star. This kernel is invariant for the unilateral shift. That is, the unilateral shift in n star is the one that sends each sequence in the same sequence, but starting with 1, 0 in front. These shift operators are isometric, but are not unitary. That's what is called unilateral shift, okay? So they actually take the domain of the synthesis operator, not in AJ, but just in the Hardy space, okay? To each sequence, you get the sum of AJ, C to the J, that is an analytic function because we start with in 0. Okay. So what can you do with this observation? Well, shift invariant subspaces of Hardy spaces has been studied a lot. It has been completely characterized by Berlin, I think around 1960. Then, using that, as soon as you call, okay, there is the Hardy space, you have several definitions, okay? One of them, that's the one I'm going to use here, is that you take a boundary values. I mean, you take the functions on in the circle that have the Fourier coefficients equals 0, 1 for the negative ones. So what does the description here? And I use this notation that probably is not so general. Sometimes they call it H2 of D, sorry. But that's the definition I'm going to use. So here are the different equivalents. And here the isomorphism between L2 of n star, you go to the series with that's in the circle, the Fourier series, and this is in the disk, the unit disk, in the open unit disk. All these things are equivalent, unitarily equivalent. So the shift, when you look, I mean, I define the shift here as a translation of the coefficient here, but if you look at the Hardy space, it's just multiplication by the variable C. Okay, so actually you can define the synthesis operator starting in the Hardy space and taking the Fourier coefficient. Okay, so now how we use this result? Well, see, if Tj of G is a frame, then U here is a synthesis operator, has to be surjective, have to be onto H. Okay, that's a theorem of frames. So if you restrict the synthesis operator to the orthogonal to the kernel of U, then you have an isomorphism between the orthogonal and H. Okay, the orthogonal to in the Hardy space, the orthogonal to a shift invariant space is called a model space because that's been used for model different situations. So now we have an isomorphism given by the restricted synthesis operator between this model space and H. So one thing that can be observed is that if you take the function that is just the power of C, this is an orthonormal basis, yes, in the Hardy space for the analytic functions in the circle. Okay. So if we project these functions on the model space, so it's a projection of orthonormal basis is a frame. So naturally we have a frame in the model space. So the idea is to this frame connect this frame with a frame that we had in H, because we have already an isomorphism given by the unitary operator. So we will denote by eta a model space. So we take this operator. This operator A that is going to act in eta is applying the shift first, the multiplication by C, But what happened is because we have the unilateral shift, we know that this is a known fact that the orthogonal complement to a shift invariant subspace is not shift invariant. Okay. If the shift was the bilateral shift, then it will be reducing. I mean, both are invariant. But in that case, no. So when you apply the shift, probably you get out of this eta, and that's why you project back again. This operator has been used and are very known, and compressions. This means that the norm of the operator is less or equal than 1. It has been studied deeply. So we don't use all the properties. We just see that if you take now the function 1 in the circle, constantly 1, and we project over the subspace eta, if we call this function phi, then phi is by this isomorphism correspond to G, and T is similar to A, where B is the restriction of the synthesis operator to the orthogonal complement. So we get this triple equivalence of the iteration of G and iteration of AJ. So this work was a paper of Christensen, Hassan Assaf, and Philippe. Philippe at this time was back in Germany and was working with Getfinder, with a postdoc in the south of Germany. So just to finish, we start to think with Ursula and Daniel Suarez, our colleague, what happened, what happened now if we take now several functions, we iterate several functions, finite but several. Actually, we proved that the conditions are going to be the same for finite or for infinite functions. So for this, the main problem was because here we were working with the Hardy space. So what will be the model space for several functions? So we realized that actually the natural choice would be, again, the Hardy space, but now the Hardy space with multiplicity. This means that are the analytic functions whose values are not just complex numbers, but are just the values are in some fixed Hilbert space. And the multiplicity has to do with the dimension of this Hilbert space. So what was a little bit different here, that when we want to try to do this theory for that case, and we have to work with Hardy space for multiplicity, we need, again, the characterization of the shift invariant spaces of these Hardy spaces. And the characterization is much harder, it's much difficult. And it was done by Lux for finite dimensional multiplicity, for finite multiplicity. And later, Halmos, in a very beautiful paper that is called Shift in Hilbert Spaces, got the result for infinite multiplicity. So we applied these results, and we got this theorem. We're still working in some properties, but what we already had is that if T is a bounded operator, general bounded operator, and we have a sequence of functions, of vectors in H, then we say that this is a frame of H, then there exists that's the way we notice, and many people notice, the Hardy space with multiplicity. That's the Hilbert, L2 of n is the Hilbert space where the function take the values. So there exists a subspace that is shift invariant. That's going to be also a kernel of some synthesis operator, and isomorphism B from beta to H, where beta is what we call the here. Okay, here I mess up with the name. Now eta is the shift invariant and beta is the orthogonal complex, the kernel of the. And we get a similar result than before. So I don't want to get you tired with that, but let me tell you, just to finish, that if now T is invertible, then we consider iterations now in C, not necessarily in N. So the natural operator in the Hertz space are the bilateral shift. And things are a little bit simpler in that case, because the orthogonal complement of the shift invariant space for the bilateral shift is also shift invariant. And then you can get a result like this a little bit much easier. I put here a definition of what it is. In this case, a Hertz space with multiplicity in the disk. So they are the functions, the series, ak c to the k, where ak now are in a Hilbert space L2 of n, with the property that the sum of square of the norm of the elements in the are finite, C in T. So I think that that's enough for today, and thank you very much for the attention, and I put here some references, and I finish with that. So I'm happy to get some questions if somebody has.
Thank you, Carlos. Thank you very much. On behalf of everyone, thank you so much for a great talk.